So today what we're going to do is we're going to review some things with complex numbers, and I want to really try to simplify this whole concept for you. Complex numbers don't have to be difficult, okay? If you have the right mindset about them. All right? I have a little visualization here for you. You have the real numbers and imaginary numbers, and then you have complex numbers. And, this diagram kind of does a good job of explaining it. But what I actually want to point out to you and want you to understand is the fact that it's not like these are three distinct things. Okay? This group of complex numbers actually encompasses both real numbers and imaginary numbers. So I'm going to fill this all in because real numbers and imaginary numbers are simply subsets of the group of complex numbers. Okay? It's like they're like subcategories. All right? Now, you'll notice down here it says the equality of complex numbers. We'll talk about that in a second. But I want you to notice standard form there. Standard form is this A plus BI or C plus DI. Usually we'll use A plus BI. The A, notice, is a real number. Okay? A is part of the real numbers. And BI is an imaginary number. Okay? So a complex number is it's a binomial, okay, that has both a real and an imaginary part to it. Okay? So the real numbers here, these are the A parts. And the imaginary numbers, we'll fit it in over here. This is the BI part. Okay? If all you have is the A part, then you're in the subset of real numbers. Those are the numbers you've been dealing with your whole life. Okay? If all you have is the part that has this I value with it, then you're in this subset of imaginary numbers. But all of these numbers can be categorized as complex numbers A plus BI. Complex numbers are really just the broadest category of numbers. Okay? So, now, in order for two complex numbers to be equal, notice what has to be true. Whoops. There we go. Okay, so we have A plus BI and C plus DI. In order for those to be equal, notice A has to equal C. Well, A and C are both the real number parts of those complex numbers, right? And then secondly, B has to equal D. Well, notice B tells us how many I's are in the first complex number, and D tells us how many I's are in the second complex number. Those are our coefficients. All right? So for two complex numbers to be equal, the real parts have to be equal and the imaginary parts have to be equal. All right? This is really useful. For example, if say you had a complex number like this, let's say you had the complex number 3 plus 7i, and you wanted to add to it some other complex number to get, say, negative 4 plus 15i. Your goal was to get that new complex number. Well, you could find this by using this same property. Okay? The real parts, the 3 and the A, have to add up to the real part of our solution. So I would know that, hey, 3 plus A has to equal negative 4. Therefore, A has to be negative 7. Okay? And then I also know that my imaginary parts have to total 15i. Okay, so 7i plus bi. And it doesn't matter if you include the i's or if you just leave them all out here. But it's got to be 15i. Okay? So if we subtract 7i from both sides, then bi must equal 8i. Therefore, b has to equal 8. Okay? So I now know that the complex number that I'm looking for is negative 7 plus 8i. That's the complex number that I want to add in order to reach my goal. Does that make sense? Okay. All right. Now, we've been talking about I a lot.
What is I?
What is I? Does anyone remember what I is?
Square root of negative 1.
There we go. A lot of you remember.
Negative 1. I remember that.
Good. I squared is negative 1. Do you remember what I cubed is?
Negative I?
1.
Yeah. Negative I.
So 1.
And I to the fourth is? 1. Okay. All right, good. So we should be able to get through this relatively quickly here. I is the square root of negative 1. Now, here's the thing. Don't ever put the square root of negative 1 in your answer.
Just put I.
Just put I. All right? If you have, say, the square root of a negative 8, take that negative out as an I. So make that I root 8. And then you can simplify your root 8. What does root 8 simplify down to?
2 or 2.
Good, 2 root 2. So this would be 2i root 2. Okay? So this doesn't have to be complicated. It's just if you see a negative in the radical, pull the I out. Okay? Now, another thing we got to understand with i's is that we're never going to leave I to a power other than 1. Okay? We're never going to leave an answer that has I squared or cubed or to the 10th power or anything like that, because there's a pattern. All right? You'll notice here, we already talked through I to the 4th power. Okay? If I were to do I to the 5th power, though, well, raising it one more power is just multiplying by I again, right? Right?
Yeah.
So this is the same thing as taking I to the 4th and just multiplying it by another I. So what does that equal? It equals I. Because I to the 4th was just 1. Okay? I to the 6th. This is just like taking I to the 4th and multiplying it by I squared. Well, I to the 4th again is 1, and I squared is? Negative 1. So I just have a 1 times a negative 1, which is negative 1. Okay?
So if it's like I to a really big power, and that power is like a factor, a multiple of 1, like a multiple of 2, or 3 or 4, then it, or if it's a direct multiple of 4, it would be always would be 1.
It will be. That's right. Yeah, if we keep going here, I to the 7th is I to the 4th times I cubed. That's 1 times I cubed, which is negative I. Okay? I to the 8th is I to the 4th times I to the 4th. Well, that's 1 times 1, which is 1. Okay? And we can keep going with this. All right? I to the 9th is I to the 4th times I to the 4th times I. Well, that's 1 times 1 times I, which is I. Okay? I to the 10th is I to the 4th times I to the 4th times I squared. That's a negative 1. I squared is negative 1. Okay? And this pattern keeps going. Alright?
I, negative 1, negative I.
That's right. Okay? Because notice here, once we get to 12, it's I to the fourth times I to the fourth times I to the fourth. That's 1 times 1 times 1, which is 1. And you see this cycle, this pattern repeating. Okay? Now. Sorry.
Did you break your pencil?
Different brother.
No.
Alright, so.
No. Wait, Mr. Hicks said no.
So, what do we do then? Let's apply this here. What do we do then if we have, say, I to the 47th power?
You see what's
Divided
divisible by
5.
first, like
Divided
4,
by
it's
4.
not, then by 3, then could you do that?
Okay, yeah, 4 does not go into it evenly. In
That
fact,
would be -5.
it's odd, right? So that narrows it down to one of two possibilities, right? What are my two possibilities?
-5.
Okay, it's either I to the first or I cubed. So it's either I or negative I, right?
I, because, wait, -5.
Well, how do we figure it out? Other than flipping a coin.
It's divisible by 3.
Hang on, what?
It's 1 away from 48.
Okay, if you think about it, 48 is a multiple of 4. We're 1 short of 48, right? So that means we're at the I cubed part of our cycle, right?
But
So-
47 is not divisible by
47 is
3.
not divisible by 3.
It doesn't have to be. Here's what it is, okay? Watch this. 47 divided by 4. It takes 4 steps to go all the way back to 1, right?
Yeah.
So, if I divide by 4, that's 11, and we have a remainder of 3. The remainder tells us how many steps through the cycle we are.
Oh, so you can just find what the remainder is.
Exactly. Find what the remainder.
And then that gives you the power. Oh.
That gives you an equivalent power, all right? So watch what happens here. Watch what happens. When we have 47 divided by 4 is 11, remainder 3. What that means is we have I to the fourth times I to the fourth times I to the fourth 11 times. Okay? That happens 11 times. Because when we divided by 4, we got 11, right? So we go through this whole cycle 11 times. The cool thing is it doesn't matter because all of those equal
1.
1. Yes, they all equal 1. The key is that last one. What's left over is that I cubed.
Which is
Because that's a
5.
remainder. That's negative I. All right?
So if you
So,
have a remainder of 0, then it's 4. It's 1.
yeah, if you got a remainder of 0, that means you have an even number of cycles, which means you ended up right on 1. Good. Okay? All right. So, how do we work with these complex numbers? Okay? Here's the beauty of this. This part right here, you don't have to mess with until you get to the end of the problem. Okay? If we are simplifying things, like these expressions here, we have complex numbers 6 minus 2i times 2 minus 3i.
No, you foil first, right?
We do, and that's what I was going to ask. I was like, if we had 6 minus 2x times 2 minus 3x, we would FOIL it, right? Well, when we're dealing with complex numbers, treat it just like a variable, okay? Treat that I just like a variable until you get to the end of the problem, okay? So I FOIL that out, and we get a 12 minus 4 minus 18, so minus 22i plus 6i squared, right? And if those were x's, we would stop, and that would be our answer.
But it's -1.
But yeah, we've got I, and we don't want to leave any i's to a power greater than 1, so we plug in the -1 for I squared. So now that's a minus 6. Okay? And 12 minus 6 is 6. So I have 6 minus 22i. Notice here, there's our a plus bi form. That's our standard
We
form.
win.
Okay? Yes.
Home run.
All right? So these aren't that hard to work with if you think of them just like variables until you get to the end. Okay? Does that make sense? Okay? Now I'm going to skip the next one. I'm going to go on to another thing here. Okay? Another thing that we've done with radicals, okay? One of the things that makes these a little bit challenging is, like we just said, we have to treat it like a variable, okay? When we're doing operations, treat it like a variable, but at the same time, don't forget these are still radicals. So for example, in this case, I have a radical in my denominator, all right? How do we get radicals out of the denominator?
Multiply.
Multiply by the reciprocal.
So you have a radical in it.
Multiply by what?
Oh, the
Complex conjugate.
Yes, the complex conjugate. So here our denominator is 4 minus 2i. What is the complex conjugate?
4 plus 2i.
4 plus 2.
It's 4 plus 2i, okay? So we have 2 plus 3i over 4 minus 2i. In order to get rid of the radical in the denominator, I'm going to multiply by that complex conjugate, 4 plus 2i. Now obviously I've got to do some foiling on both the numerator and the denominator. Okay? Take a minute here and try simplifying this the rest of the way on your own.
So you have to
Okay.
multiply it by 20 so that there's no denominator.
No, you just.
No.
For 10.
We need it in standard form. Okay?
Put 2i plus 3 instead of 2 plus 3i. That helps so much.
So remember, standard form is a plus bi. So really,
Solve more problems.
what we need to do is we just need to separate this into a real part and an imaginary part.
Oh, one.
So would it be 2 over 20 plus 16i?
2 over 20
Plus 16i
over 20.
over 20 as well.
Okay.
They have a common denominator. I'm just splitting it up. So now I can write that as 1/10 plus 4/5 I.
Master. Can you write like 4/5 I? Like
You could do,
a large
like I
I?
have it here, the I is big like this.
Yeah, never mind.
Or you could write that as 4i over 5.
4 over 5i.
Okay?
Is
You
4
can't do it 4 over 5 with the I underneath.
Okay.
So the final answer is 1/10 plus 45.
That's correct.
Let's try some.
Okay? Okay? So, we can try some here. Don't forget how to handle
This one's long.
adding fractions. What do you have to have in order to add two fractions?
Common denominator.
Common denominator. So question, should I get the radicals out of the denominator first and then add them? Or should I try to add them and then get the radicals out of the denominator?
Get the radical out first.
No, no, because it might
was
go into
complete
an I
guess.
squared, which is a -1. And there's no
But that's
radical at the
okay.
end. Exactly,
Let's do it
so.
Either way.
Get a
What,
common-
You
Rebecca?
can do it either
Get
way.
a
You could do it either way, it doesn't really matter.
Okay.
Okay? Whichever way you want. What you were saying is correct, Samoa. If you get rid of the radicals first, your denominators aren't going to have any i's in them, which you may prefer because you may find it easier to get your common denominators when you're not having to mess around with the i's. Okay? Other people like to just get the common denominator first, get it all in one fraction, and then mess with getting rid of the radicals in the denominator. Either way, it doesn't matter. Okay? On the very first one here, what would you do first? The 5i over 2 plus 3i squared.
Sorry?
4 over 2 plus 3i squared, and then you take the complex conjugate and multiply it by.
Okay, so first of all here, we're going to FOIL that denominator. So we have 5i over, what do we end up with?
4
Plus 9i squared.
Are we going to FOIL? 4 plus
6i.
6i plus
6i.
6i. So we got a plus 12i, right?
Yeah.
Okay. So now we've got 5i over, what does that denominator simplify to?
4 plus 12i minus
5
9.
plus 6i.
Okay, good. 4 plus 12i minus 9, that's a negative 5 plus
12i.
the 12i. Okay,
Then you multiply it by negative 5 minus 12i.
there we go. Our complex conjugate, we have 5i, or I'm sorry, we don't need the I. We need negative 5 minus 12i, negative 5 minus 12i. Okay, and you take it from there. Okay. So you do your multiplying, then you sub in negative 1 for your I squareds.
Wait, and then what would we do here? Oh, yeah, that makes sense.
Okay. Okay. So now we've got our answer in standard form. 60 over 169 minus 25 over 169. The 60, well no, 169 is 13 squared, so that's not going to reduce. Neither of those fractions are going to reduce, so we're done.
You got there for 1 second.
Yeah. So that wasn't too bad, was it? Okay.
Question.